Okay. We'll see.
Ms. Bauer, are we doing notes today?
A little bit. And then we'll have some extra practice.
Yes.
Okay. All right. So last night I asked you to view kind of the remainder ways that we can estimate the area under a curve. We did the left endpoint rectangles and right endpoint rectangles together. And the ones last night were the midpoint and the trapezoid. Okay, how's she doing? Good. All right, so the results from the Google form were very optimistic. Okay, we're feeling pretty good with this. Kind of simple. It's just like area formulas and adding numbers up. So I know we can do that. We're going to go over kind of different formatted types of questions today. And what we do today is actually more commonly found on the AP exam than what we were doing yesterday. Okay, we looked specifically at graphs yesterday to visually understand what we're doing or kind of how these Riemann sums work. Today, though, we're going to take a look at tables. And tables are more commonly found on the AP exam than graphs. I have never seen, okay, in my career or when I look back to previous exams, I've never seen them ask you physically draw in rectangles or trapezoids. So if you don't feel comfortable doing that or you kind of get confused on where to plot the points or how to draw them, that's not that big of an issue. Okay, but I'm hoping from yesterday and last night that we're at least understanding the calculations, what we're looking for, and kind of how all that relates together. Is that a fair assumption on my part?
Yeah.
We're doing okay? All right. So on page 356, I want us to just go ahead and fill in this summary table of what we did yesterday and last night. So we did all of these types of sums. These were all of our approximations, and this is what we stated as either an over or an underestimate. So we're eventually going to get to the point where we're going to be able to figure out the exact area by hand. That's actually going to be in our next section, but for now these are our estimates. So can we perhaps put a star next to the one that we think is the closest to the actual one? Can we just take an educated guess?
Trapezoidal of 1 unit.
Of one? So this one?
Yeah.
Okay.
Left-handed half.
Left-handed half.
Wrong.
Oh wait, no, that one's further away.
Yeah.
Okay.
We're either looking for the lowest overestimate or the highest underestimate.
Do we know
So
we're doing?
It's 40.
What was like 40?
The midpoint.
Nah, it's 39.7.
I'd say these two are fairly close together. Okay, the question is it actually 40? Is it actually 40.02? Is it actually 39.9? You know, so it's going to be somewhere in between these. The question is, which one do we think is the closest? So it's just an educated guess. Which you like the trap better? Okay, maybe we'll put a star by that one. Okay, so the two big things that I saw in the Google form last night were, one, will we ever have to draw the actual rectangles or trapezoids? And the answer is usually no. Okay, on the AP exam, most likely not. I mean, we should still be familiar with it, but it's probably not going to happen. The second question is, how are we able to tell if it's an over or an underestimate when the shapes are very, very thin and it's difficult for us to actually see on the graph if it's above or under the curve? You know what is meant by that question? Okay, so we're going to explore a little bit today, kind of at the bottom of this page in the little strip, how we can tell if it's an over or an underestimate when we have very thin shapes, okay, where it's visually kind of difficult to determine. So in this little strip, can we divide this into 3 sections, okay, because we've talked about, I know we did 4 different types. We did left, right, midpoint, and trapezoid. The midpoint, though, is usually going to have a little bit of both over and underestimate, because if you do something in the middle, the left-hand side is either over or under, and the right-hand side is the opposite. So it's going to be a little bit of both either way. The other three, though, we should be definitely able to tell if it's an over or an under, depending on the type of graph we have. So here, we'll take a look at left endpoints. Over here, we'll do right. And for the last one, we'll talk about the trapezoids. So for a left endpoint rectangle, I want us to think about what if we were to draw those on an increasing function, and what if we were to draw those on a decreasing function. Okay, if we did left endpoint rectangles on our first function, maybe we'll draw.
Could you try again?
Nope.
I think we're sharing a little.
If we, okay, so this is what our rectangles might look like on a left endpoint for this increasing graph. If we do left endpoint on a decreasing graph, though, it's going to look something like this. So what if we have left endpoints on an increasing function, over or under estimate? Definitely under. Okay. What about decreasing? Definitely over. Okay. So if we're able to determine, or they actually tell us that a function is always increasing or always decreasing, we know exactly our estimate as over or under depending on what the case is. Okay. That's assuming we use left endpoint rectangles though. Okay, let's go ahead and try right endpoints. We're going to look at the same increasing and decreasing function. All right, so right endpoints means the right vertex touches the function. Over or under for increasing? Over. Over or under for decreasing? Under, right? Kind of switches. Okay, so that's for left endpoint versus right endpoint. All right, let's try trapezoid. Now for trapezoids, we're not necessarily going to look at the increasing or decreasing nature of a graph. We're going to look at the concavity. So let's maybe try a concave down and a concave up. So if we started to draw trapezoids, okay, underneath a concave down graph, we could probably put one dot here, form the bases, and then connect the dots. If we drew another one, butted up against it, maybe there's a dot here and a dot here, form the bases, connect the dots. That's definitely under. Okay, let's try trapezoids on a concave up. So maybe put a dot here, base, base, connect the dots. If I draw another one, connect the dots. Over or under? Over, yep, because we're including some area right here that we really shouldn't be. Okay, so in a trapezoid instance, we're more concerned with the concavity of the graph to determine over or under, but for left and right rectangles, it's the increasing or decreasing nature. So if we have that piece of information available to us, we'll be able to say for sure if it's an over or under estimate. If they don't mention anything about whether if it's just increasing, just decreasing, or what the concavity is, we can't say for sure if it's an over or an under estimate. Okay, we have to have that information available to us. Do those visuals make sense?
Yeah.
Can we see it? Okay, so let's take a look at page 357. Okay, we're going to take a look at how we can use these Riemann sum calculations to help us estimate the area under a curve, but instead of having a physical graph, we're going to have a table of values to go off of. So we're going to have to be familiar with kind of what to look for in the table to help us determine the little individual areas that we're eventually going to add up. So if we look at the first one, it says approximate. Now if you look at the notation, okay, if we kind of read it out loud, we would say the integral of f of x from 0 to 25. So the integral is meaning area under the f of x graph. The area is going to start at the x value of 0, and the area is going to end at the x value of 25. So those numbers on the top and bottom are giving you the interval or the bounds. So looking at the table, x value of 0, x value of 25, it looks like we're going to have to go all the way through the table for this case. So to help us with this approximation, we're going to use a midpoint sum of 3 subintervals. Can we possibly break up this table into 3 sections so that we can analyze each one individually? Can we maybe say where the first section would be? Yeah.
I'm thinking it's 0 to 4 because it's positive, and then 7 to 15 to negative, and 20 to 25.
Okay, so your first rectangle would go from 0 to 4, but your second rectangle would go from 7 to 15. So if you think about the x-axis, you're going to have one rectangle in here, but then you're going to have another one here. You're missing all of this space between them, right? So wherever one rectangle ends, you want the next one to immediately begin at that spot. Remember when we drew them yesterday, they were all butted up against each other, they shared a side. Okay, so wherever one ends, the next one has to begin. So can we break it up into 3, possibly a different way? Yeah?
0 to 7,
Okay.
7 to 15,
Yep.
and 15 to 25.
There we go. Okay, where one ends, the next one begins. So the integral from 0 to 25 of f of x dx is approximately. Okay, now in this table, we have to think about which numbers are representing the base of the rectangle and which number is representing the height of the rectangle, and they specifically want us to use a midpoint, okay, a middle point to help us get that height. So in this first rectangle that we would draw, where can we look to calculate the base length? Your x values, okay, so from 0 to 7. So our base is 7. Your height comes from a y value, so that's going to be our f of x row at the bottom. Looking at from 0 to 7, okay, so these 3 y values right here, which one can we use to represent a midpoint height? 6. Okay. Now, this brings into question, our base goes from 0 to 7, but notice how the middle value we know has an x value of 4. Is 4 the exact middle of 0 to 7? No, it doesn't have to be. I know in the graphs you did last night, we were able to use the exact middle, but that's because we had a physical function or equation to use to help us. In this table format, the midpoint you use might not be the exact middle of the interval. Okay, that's okay. You're just choosing a midpoint, okay, some point in the middle of that interval. Does that make sense? It's okay if it's not the exact middle. All right, so here's the area for our first rectangle. Let's try the next rectangle. So the next rectangle we said goes from 7 to 15. So our base length would be 8. Okay. This is also something different from the graphs. Okay, when we did graphs, didn't we have each rectangle have the same width all the way through? In a table format, we might not have that luxury because it just depends on the information that we have. So when you have a table, the base widths might be different. What about the height from a middle point? -10. All right, and then our last rectangle goes from 15 to 25, so that's a base of 10, and if we use a middle height, that'd be 8. Okay, so calculation all the way through will approximate our area. 42. There we go. So we don't have an equation, but we don't have a graph. We do, however, have an estimate as the area, or for the area under the curve. Yeah.
I'm just kind of confused. How come we didn't use -5 for the midpoint in the second one?
Because the second rectangle goes from 7 to 15. If you use -5, that would be a left endpoint.
Okay, so we're not using the y value in the middle. We're just using like the closest to the actual center.
Right. So if you just, so for this second rectangle, you're going from 7 to 15. So this is a left endpoint. This would be a right endpoint. So this value is something we have in the middle. So if this is the middle value, we're going to use the middle height. All right. Let's try the next one. Approximate the area under the f of x graph. We don't have an f of x graph, but we do have an f of x table. It happens to be the same one as before. This time, though, we're going to go from 0 to 15. So for your table, notice how the last two columns don't really matter. So maybe block them out for this question. Okay, so to help us with this approximation, we're going to use a left-hand Riemann sum with 4 subintervals. Can we divide up this table into 4 pieces? So that where one rectangle ends, the next rectangle begins.
0 to 4, 4 to 7, 7 to 12,
12 to 15. There we go. Okay, so our first rectangle goes from 0 to 4. That's a base of 4. And we want to use a left-hand Riemann sum, so we need the height from the left side of that rectangle. 15. Okay. The second rectangle goes from 4 to 7, so base of 3. Left-handed height is 6. I think it helps, at least it helps me, to draw the rectangles at the top for you to see what the left or the right or the middle is. Okay, the third rectangle, 7 to 12, 5. Left height is -5, yep. And last rectangle, base of 3, left height, close, -10. All right, calculation, 23. All right, now if we read the directions at the top, it doesn't necessarily say anything about the characteristic of this function f of x. It doesn't say only increasing, only decreasing, only concave up, only concave down. So we can't really tell for sure if these are over or under estimates because we don't have that information available to us. Yeah.
How can we use like negative numbers when we're multiplying? Because like, what if you got a negative area? Like, can that happen?
Can we think about what that means? If the area under the curve is negative, it's underneath the x-axis. So that would be like, if I had this parabola and I wanted the area from A to B, that would be this. Okay. So I know like physically negative area doesn't make sense, but now we're talking about location.
Yeah.
Okay. All right, let's try the next one. Approximate the area from 4 to 20. So we're going to ignore 0 and ignore 25. Use a right Riemann sum with 4 subintervals. All right, we'll go from 4 to 7, 7 to 12, 12 to 15, 15 to 20. Good, Griffin?
That picture that you just drew, where it's under the x-axis.
Yep.
If it came back up and then went back down, it was like the same area. Would the area just be 0 then?
Mm-hmm. If you have equal amount of area above or below, one's negative, one's positive, so it'd be 0. We're actually going to get into that in a few sections, dealing with properties. Okay. Okay, so let's see. From 4 to 7, 3 unit base. If we want a right endpoint height, that would be -5. From 7 to 12 is 5. Right endpoint would be -10. 12 to 15 is 3, right endpoint -2. 15 to 20 is 5, right endpoint is 8. -31. All right. We doing okay? Do we think the table format's a little bit easier than the graphs?
I don't know.
We don't know.
I don't like drawing the bars. I like a lot.
You didn't like drawing them?
I don't like
It was tedious. It was tedious. But we had to understand the visual for us to kind of make the connection to here, like which numbers represent base, which ones represent height, all that jazz. All right, 0 to 25, so the whole table using a trapezoid sum with 3 subintervals. So 0 to 7, 7 to 15, 15 to 25. All right. Area of our first trapezoid. We need 1/2 times the height times the sum of the bases. Where can we look in our first trapezoid from 0 to 7 to find the height? When you drew your trapezoids last night, where was the height located on the graph? That's the bottom. That's the x-axis. Yep, kind of counterintuitive because we think height means y, right? But in terms of these trapezoids that we draw, it's actually the x. So 0 to 7 would be the height. Where are we going to get the bases from? The heights on the ends. Yep, so 15 and -5. Okay, so there's our area for the first trapezoid. Let's go ahead and add the next one. So the next trapezoid goes from 7 to 15. That's a height of 8. And if we add the bases, we're going to have -5 and -2. Okay, last trapezoid, 15 to 25. That's a height of 10. The bases are the 2 ends. So -2 and 20. All right, let's get our approximation. Any luck? $90. I got 7. Close. All right, 97. So notice how these are all approximations. Some of them are different though, like this one was from 0 to 25, this one was from 4 to 20. Okay, but we don't really have enough information to determine over or underestimate. I do want to take a second though and try some of these. All right, we're going to skip the one at the top for now. We'll come back to that if we have time in a moment. But I want to take a look at the table example at the bottom. Okay, approximate the area under the curve described by the following table of a strictly increasing, and I want you to add in there, and concave down. Okay, so go ahead and make a little addition in there. So strictly increasing and concave down function using the following Riemann sums. Okay, so we're going to do kind of one of each. When appropriate, so when you can, provide a justification for when your approximation is an over or an under estimate. Can I give you about 7 minutes or so to try to do the 4 of these? Yeah? Go ahead and try them out. How did we do?
I got a 44 for the first one.
Did you? Let's see.
Yeah, that's 44.
Yep.
Nice one. Great copy.
Good catch. The rest look good though?
Yeah.
Yeah? Okay. So, based off these approximations and the fact that we know something about the graph of f of x, can we determine if these are over or under estimates? If we use a left endpoint on an increasing concave down graph. Under, because f of x is, which one of these is more important for left? Increasing. Okay, if you actually wanted to draw a picture of this, if we're only increasing in concave down, we probably look like the left side of an upside down parabola. So if you draw in a left endpoint, you're definitely going to be missing some area. All right, what about a right endpoint? Over, because f of x is increasing. Okay, so if you try to draw in a right endpoint, notice how that would be an overestimate. Midpoint, let's see, if I do, I'm going to draw this again over here. If I do a midpoint, probably. Okay. We would say, can you give a reason though? Provide a justification.
I would say because it's increasing and concave.
So you think both have an influence? Okay. I mean, an educated guess, probably sure. So based off the picture, but who's to say that this is the only type it could have? Like you could have maybe a drastic exponential curve like that, right? And if I did a midpoint, that would be pretty darn close to being the same. Over here, though, still might be a little bit over. Okay, so maybe we'll say over because based on the increasing and concave down property. Okay, so the moral of the story is the midpoint is going to be a little bit difficult because you might need both pieces. Maybe drawing a picture will help you determine that, but we can't really say what this is as certain as we can the other ones because you need a little bit more information. What about if we drew a trapezoid? Under, okay. So point here, maybe point here, bases, connect the points. Definitely under. Yeah.
If D was under, wouldn't C have to be under because it's less than D?
If D was under, wouldn't
C have to be under because C is less than D?
probably.
So it's
Okay. So under under because f of x is concave down. So if this is under, it would have to be more than this. So then this would have to be an underestimate as well. Okay. So under. Maybe we'll just cross that off. Like we don't have enough information. Like if the only one they asked you to find was the midpoint, and they asked you, so we'll go ahead and say we didn't know this. If the only one they asked you was a midpoint, would you have enough information to help you determine if it's over or under? No. You'd have to do other estimations to get an idea, okay? But the point is, the midpoint is the question mark of the 4 types that we have. Okay, if we know increasing, decreasing, concave down, concave up, the other ones are for sure over or under. Midpoint is the gray area. How do we do? Pretty good? All right, can we do the top one real quick? We still have some time before the bell rings. Approximate the area under the curve illustrated by the left side Riemann rectangles. Can we write what the notation should look like? The integral of f of x dx,
Negative 3 to 1.
-3 to 1, okay, so -3 to 1, is approximately, they drew in the rectangles for us, so they're nice.
Yeah.
Our base unit is 1. The height from the first rectangle is 12, okay, using its left endpoint. Next rectangle, base of 1, height of 7. Fourth rectangle, base of 1, height of 4. Last rectangle, base of 1, height of 3. Okay? Approximation. 26. There we go. Looks good. Doing okay?
Oh, yeah.
All right, these were all approximations. Okay, we're eventually going to get into the exact value, and we're going to check that out tomorrow. Speaking of tomorrow, though, who's going on the field trip? Who's not going to be here?
Everybody.